So I'm here to present the work HaPPy. It's called Hyperthread-aware power profiling dynamically. The name is really long. So it's collaborating work with Xiao, Zhang, and Stephane Eranian from Google, and Lingjia, Tang, Mars from University of Michigan. This work is largely motivated by the fact that we really need the per job power profile in the data center in order to improve the power management system. To very concrete scenario to make use of the per job power profile can be the power camping system and the energy-based billing. For power camping, I believe most of you may have known that data center is built upon the over-provisioned power supply, which means that you can never turn on all the machines and run them at full scales. That will just make your power supply explode. And so at some point, you may have run so many jobs that your power usage will approach a dangerous area, so that you need power camping system to get involved to throttle and kill jobs. At this time, there's a problem which of the job you're going to kill and throttle. So with per job power profile, you're going to make better decisions so that you can make flexible choice and make better power camping system. Another possibility of using the per job power profile is the energy-based billing. So as cloud is becoming more and more popular, it's reasonable to think about, do we charge user by the resource they use, or we charge them by the energy they use? This is an open research question and worth you think about, but it's not the content of this talk, so I'll skip this. And for this work, we mainly focus on the CPU power, which occupies more than 70% of the total power usage in the typical high-end server. But even for this simple CPU power accounting, there is a significant challenge, which is when hyperthreads is present, many of the past research assumption does not hold anymore. The power characteristic is not the same. And we're going to look into what's the problem here. So the current common practice of the CPU power modeling believes that the CPU power is actually linear to the CPU usage. So as long as you're, in other words, the CPU power is linear to the cycle executed on the CPU on the physical CPU, and we did experiments to repeat this assumption. And here we have a Sandy Bridge machine with one CPU socket and 8 physical cores on each of the socket, and there are 2 hyperthreads on the physical core. We're going to use only one first hyperthread of each physical core. We gradually fill the workload on these physical cores. And we selected several Google applications to validate the result. The application we use are Bigtable, web indexer, a YouTube application, and the image processing application, and the MapReduce-based log processing, and the RPC benchmark. Due to the confidential reasons, some of the name are not allowed to talk publicly, so you see it's web indexer or whatever. So the result is as expected. So when you just use one hyperthread, the power curve just grows linearly. So you see the blue dots, it's consistent across the applications. But the problem is when hyperthread is present in all this is not true anymore. So we did similar experiments. This time we use both hyperthread on each of the physical core. So we use 1, 2, 3 until 8. And the experiments as shown in the figure. So this time it's the red dots. And you see there is actually 2 different curves. These are 2 extreme cases. So when you mix the workload, use both hyperthread and using just one hyperthread, it's expected to fall into this shaded area. So you can no longer just, when you are doing per job power profile, you cannot directly break the total socket power by the CPU cycle they use. It's not true anymore. So in this work, what we do is a model called HaPPy. HaPPy, what does HaPPy do? It's a three-step work. First, we can obtain in current architecture, we could obtain the hot socket power. Intel has shipped the CPU hardware counter in order to count the power on the fly. In the future architecture, there may be a finer granularity counter, so we can jump to step 2 directly. But currently, we still need a step 1 to break down the socket power to each of the physical core. And then when we have the core power, we're going to break down the core power to each of the hyperthread running on. And when we have the hyperthread power, we can map this power to each of the job. So the key observation to solve this problem is our so-called RHT factor. The reason we define this is we observe that when you use both of the hyperthread, you always have more power. Slightly more, but it's never twice as much as you use 2 physical threads. So you can see here, if we observe the previous experiments, but change the access or to the number of the physical core, you can see the red dots are always slightly higher than the blue dots. We empirically measure these results using applications, and the result is about this difference is about 1.1 difference. And we expect this methodology can be used on the public platform. And actually, we have done this on public machines to reproduce the result. But the result can be checked out in our paper if you're interested. The reason that leads to this RHT factor is because of the sharing of the core. If we break down the execution of the physical core, you could notice that here are 2 hyperthreads executing in a core. The blue parts are each thread executing exclusively, and the red parts are they executing sharely. These red parts, we believe, are the major reason that lead to the slightly power increase. In current architecture, we could capture the cycles executed by each of the threads, cycle 1 and cycle 2, and we can also capture the cycle executed by the whole physical core. This requires some dirty trick inside the performance counter, but if you're interested, I'm going to tell you how to do that. And using this, we could capture the overlap cycle and the non-overlap cycle. So using this, we could define the weight of each core. As we mentioned before, that the overlap part may consume slightly more power. So naturally, the weight of each core can be defined by the unoverlap cycle plus the overlap cycle, but multiply the factor we defined before. And using this core weight, we can break down the CPU, the whole socket power to each of the physical core. Similarly, we could do the same to the hyperthread. So when one hyperthread is executing exclusively, it will be charged for the full power during this period. But if they are sharing the core, they will be the power will be break down to half. Each will be charged by half. And we can define the weight of the hyperthread. And using this weight, we can further break down the power of hyperthread, break down the power of the core, and assign to each of the hyperthread. So the third step is involving mapping the hyperthread power to each of the job. Because this talk is time budget is really short, so if you're interested, we can discuss this offline, and it's also discussed in the paper. There are many aspects, including the context switch and other factors that we need to consider. But naturally, we could do this to assign the hyperthread power to each of the job. So for evaluation setup, we use one Sandy bridge machine with 2 CPU sockets. Each socket has 8 physical core, and we use just one socket. Another socket is used to run some system demos, so noise will be lower. And from the Linux kernel we run, at that time it's still an internal kernel, but right now it has been merged into the upstream kernel. So all the power counter access feature has been patched into the 3.14 kernel. You can download and use it and try it yourself. And the application side, we use 6 Google applications, and we pair these applications together. So each of the pair will contain 2 applications. One will use just one hyperthread on the physical core, and another application will use 2 hyperthreads on the physical core, and we pin them on the CPU. And we gradually increase the number of the pairs to observe their power behavior. And to observe the accuracy of our prediction model, that we set up our Oracle data. That means when we have several workloads running there, we're going to make a prediction And with this prediction, we remove several of the jobs. There will be power delta. So we compare the power delta with our prediction results, see how much difference they are. The model we compare are the common practice model that we just it will just consider the CPU cycles executed on by each of the job and directly break down the hot socket power linearly according to the CPU cycles. And our model is trying to take aware of the hyperthread and make a prediction. The result here, for Google application, we have 3 pairs of result. We pair big table and image processing together, and web indexer with MapReduce, and YouTube with RPC. So both from average case or from the maximum case, it's as expected, our model improved the error largely. It's improved by, you can see the number can be even improved by 50. But you may argue that the absolute number is just several watts, like 5 watts, 10 watts. But just think about it. It's per job bus. You can think about how many jobs there are inside a data center. So this kind of accuracy improvement would be very great improvement inside the data center. We also have spec CPUs result in our paper, but due to time limit, I didn't put it here. So if you're interested, we could you could check a paper, or we could discuss about some details of the setup, if like some kind of how do we run applications and how do we obtain the result. So the conclusion is basically you can never ignore the hyperthread there. So this is largely ignored by many of the previous studies. They just turn off the hyperthread, but this is not true inside the real data center, because hyperthread means you gain some kind of performance throughput improvement, like 10 or 20%. You can never turn it off. You have to cope with this problem. So in our contribution includes that we propose a practical method how to measure the hyperthread and model the hyperthread. And we evaluate using the real application. It's not just kernel program that try to mimic a certain aspect. It's a real application that link to the production database, production code base. And the accuracy can be improved a lot. And there are some details. If you are interested, please just check the paper. And this is my talk. Thank you very much.
Nice talk. Joe Greathouse from AMD Research. So this is not an AMD-related question, but a Google-related question. So Google is not just using Intel cores anymore. They're also looking into Power cores, which run many more threads in their SMT systems. Do you think that this methodology will work when you're going up to, say, 8-way SMT?
I know you from AMD, but actually about how Google use these things or whether they use them, I'm not sure I can answer here. I have my mentor there. You can talk with him to see.
So let me rephrase the question. I don't care if Google's using Power cores. They've announced that they will be. The question is more, will this work for large-way SMT rather than just 2-way SMT in Intel cores?
I believe that currently we just look into the Intel machine, but right. The same method could apply to, because we just want to capture the shared state. Mm-hmm. So once we could capture the shared state, we could model the multiple SMT cores, and it can work in the same similar way. I believe we could do it.
Thanks.
You'd have more combination options, though, as you go across.
Sir, could you?
Just the follow-up to his question. You'd have more combination options, right? So you'd start to have a space. Christopher Stewart from Ohio State. Great talk. Love it.
Thank you.
I was interested in the ratio between average estimation error to the maximal estimation error. It was actually pretty low. So I was wondering, which is great. That's a good thing, assuming you did everything right. So I was wondering if you looked at phase changes in the applications over time that would possibly cause your maximal error to tick up.
You mean, let me rephrase. So you mean that the application's power characteristic will just change so that
exactly, such that what you're subtracting as the hyperthread time would change, right?
Yeah, that's a good question. That application itself will have a power characteristic, but right now we just this work is mainly looking to how to capture the power characteristics during the period we sample them. As to how to make use them, it's another question we are right now looking into. So we should consider that you may see a curve of the power goes like a flat line, then goes up a little bit and go back to flat. But it's not how do we model them. We can capture this kind of change when it changes, but how to use them is a different question, I think. Thank you.